Okay, the quiz. It's now too late to submit the quiz, so that means I can go over the answers. Um, some of you actually did more work than was necessary, but be that as it may, that's fine. Okay, so key ideas for number one, outside function was the sine. So sine cosine tangent x, derivative is cosine cosine tan x, times the derivative of this, which is negative sine tan x, times the derivative of tan x, which is secant squared x. Okay, so this is essentially it. You can rearrange it, and some of you rearrange other ways. That's fine. Okay. Number two, some of you did logarithmic differentiation. That's okay, but it's more work than you really need it. You didn't have to do logarithmic differentiation. If you just realize when you have 2 to something, the derivative is 2 to the same thing, ln 2. And then by the chain root times the derivative of this, which happens to be a product. So x squared times derivative of secant 3x is secant 3x times tangent 3x times the derivative of 3x, which is 3. Then plus the second function, secant of 3x times the derivative of the first function, which is 2x. And that's essentially it. Again, you can rearrange. Okay, I did my own rearrangement. You didn't have to rearrange it exactly the way I did it. That's a 2x there. Sorry, I originally put 2x squared. That's a mistake. It should be 2x. Okay, so if you didn't have exactly what I had, but it was equivalent, that was fine. Okay. Okay, 3, the best way to do that was implicit differentiation. So the derivative of this is 4x squared times 2y dy dx plus y squared times the derivative of the first function, which is 8x. And in the derivative of this, think of it as plus negative 5xy. I think it's easier that way. So first function is negative 5x times the derivative of the second, which is dy dx, plus second function y times the derivative of the first, which is negative 5, equals the derivative of the right-hand side, which is 0. Okay, then I put all the dy dx's, leave it on this side. I get 8x squared y minus 5x times dy dx. And throw that over, 5y minus 8xy squared. Divide both sides by this. So I would accept this 5y minus 8xy squared over 8x squared y minus 5x. It just so happens that if you factor and cancel, the cleanest way you can get it is to be negative y over x. Okay, but I would accept it like that. Okay, then number 4, to differentiate this, you go 1 over that, 1 over x squared plus 4 times 2x. And then this one, which is a quotient root, x plus 1 times 1 minus x times 1 over x plus 1 squared. Okay, you could have left it like this. Some of you took the trouble to get a common denominator. That's not required for stuff like that. Just leave it like this. That's fine. So if you went ahead and did more, that's fine. I was just looking mostly for this. And that was that for the quiz. Okay. All right, so I know some of you just recently submitted the quiz. I'll get that eventually. As I mentioned earlier, if you submit the quiz early, I probably already got to it. In some cases, if you didn't get full credit, you had a chance to recorrect it and resubmit it. Okay, but if you just submitted it a short while ago, then it's just a one-shot deal. And that is that. Okay. All right. We haven't had a break, quote unquote, in a long time, meaning 5-day weeks have been the norm. We haven't had a break since Labor Day, I think. So 5 days, 5. Now the holidays, quote unquote, begin. Starting this week, there's a, well, I call it a one-day weekend. Thursday the 15th is a flex day. So teachers have to work, but you guys don't. So this week, Monday, Tuesday, Wednesday, and then Friday. Okay, and so we're aiming for the next exam Friday the 23rd. Okay, and yeah, once November hits, the holidays start coming up. We have a Veterans Day holiday. There's Thanksgiving, and so before you know it, we're done, and the Christmas holidays and all that. It's pretty soon. Okay, so we're roughly halfway through the course now. I believe we have 8 weeks down, and there's 9 weeks to go, but those 9 weeks include a lot of holidays. Like I said, if you count all the flex days and Thanksgiving and Veterans Day, it's pretty much 8 more full weeks. So we have 9 weeks per se, but not all of them are 5 days. Okay, so I'm going to do 3.7 today. I think I'll be done with 3.7 today. And who knows, maybe I'll sneak in a little 3.8, but we'll see how it goes. Okay, so no school on Thursday. Our next class is Friday after Wednesday. Okay. All right, so 3.7 is a lot of word problems, okay, applied problems using the derivative. Okay, and we said there's applications from chemistry, biology, physics, economics. The book goes over some of those. Okay, so it's just 7 to 19 odd. I'll do a bunch, and that's what the aim for is today. Okay, so 7, the height in meters of a projectile shot vertically upward from a point 2 meters above the ground level is, according to this formula, this is all we need. H equals 2 plus 24.5 t minus 4.9 t squared after t seconds. So we have meters and seconds. Okay, where am I? I'm on page 233. And yeah, for those of you that want to get this on the video, so 7, 8, 9, there's 11. Okay, then the next page. Some problems there. And a little more. So again, you can always get these off the video. A little bit more. And some more. And I think that's all we needed to do, right? Okay. Yeah, it was what, 7 and 19 odd? That's it. Okay, so velocity is the first derivative. Acceleration is second derivative, we know, right? Okay, so find the velocity after 2 seconds and 4 seconds. Take the derivative, plug in 2, plug in 4. Okay. When it's a projectile reach its maximum height, okay, well, if you think about it, when you throw something up in the air and it comes back down, the maximum height occurs when the velocity is 0. So I'm going to be setting the velocity equal to 0. Okay. And then it asks, what is the maximum height? We'll just plug in for the t. Right, so let's take a look at what we got now. So here's the height function. H prime is the velocity. So the derivative of this stuff, the derivative of 2 is 0. Derivative of 24.5t is 24.5. And the derivative of that is minus 9.8t. So that's the velocity. Now, if it asks for the velocity at particular moments in time, just plug in 2 and 4. So velocity at 2, 4.9 meters per second. Velocity at 4, plug it in, negative 14.7 meters per second. And what's the significance of the negative? Negative means you're going down, right? So positive means you're going up. Somewhere the velocity is 0. If you stop and think about it, if something goes up and then it comes back down, right at the very top, the velocity just for an instant is 0, right? Before that, it's positive. Then after that maximum point, it's negative. Okay, so again, to solve for part B, when does projectile reach its maximum height? At the maximum height, when I throw something up and it comes back down, that maximum height, the velocity is 0. So I set the velocity equal to 0. So 24.5 minus 9.8 equals 0. Comes out to be 2.5 seconds if you solve there. Again, anything that's just a calculator thing, I'll just let you do that on your own. You can punch it in the calculator as well as I can, or better, right? So 2.5 seconds, this thing goes up, and then it starts coming down. Right at the very top, that was 2.5 seconds. That's where the velocity is 0. Now, what is the maximum height? I plug in 2.5 there and there. Okay, so h of 2.5, plug in 2.5 to the original function. So 2 plus 24.5 times 2.5 minus 4.9, 2.5 squared, 32.625 meters. Okay, part D, when does it hit the ground? Okay, hits the ground means height is equal to 0, right? If something hits the ground, height is 0. So I set this thing equal to 0. So 0 equals negative 4.9 t squared plus 24.5 t plus 2. I rearrange it so that t squared comes first, and then t, and then a number. Okay, and it basically becomes quadratic formula after that. So I decided to multiply by negative 1 because I like my a to be positive. So multiply both sides by -1. 4.9t squared minus 24.5t minus 2 equals 0. And so I'll just say, etc. Plug into your quadratic formula. If t comes out to be negative, throw it out. T can only be positive. Okay, so I'll just say, etc. So that gives you the t. And then, with what velocity does it hit the ground? Okay, so when you hit the ground, you have a certain t. So the answer to part D, you get t equals blah, blah, blah. Okay, then plug that into the velocity function. Okay, plug it back into here. And that'll give it to you. Okay. So that's as much as I wanted to show you for that one. And then I believe number 9 is very similar. So I'll let you do 9 on your own. Okay, 11. Okay, so 11. A company makes computer chips from square wafers. That. Wants to keep the side length close to 15 millimeters. I've got X here. How does the area change when the side X changes? Find A prime of 15, explain what it means in this situation. Okay. So what I got, so we have a square wafer. It wants to be approximately 15, but in general, I call it X. So area is X squared. All right, so it asks, how does the area change when the side changes using the Leibniz notation that's dA dx? Rate of change of area with respect to X. That's one of the advantages of having the so-called Leibniz notation, dA dx. Okay. The wording was, how does the area change as I change the side length? That's dA dx. So dA dx is just 2x. That's easy. So we have 2x. Okay, then it says find A prime of 15. I just plug in 15. A prime of 15, 2 times 15, which is 30. So 30 millimeters squared per millimeter. You can change that to 30 millimeters, but it's really 30 millimeters squared per millimeter. So that means when I'm at this length, if I'm already at 15 millimeters, if I change the length by 1 millimeter, the area will change by about 30 square millimeters. That's what it means. So rate of change of area with respect to X. So if I change this by 1, I change this by 30. Okay? So right at a length of 15, if I increase or decrease the length by 1 millimeter, I change the area by about 30 millimeters squared. Okay, what about part B? Show that the rate of change of the area of a square with respect to its side length is half its perimeter. It sounds like a lot of verbiage, but it's actually very easy when you stop and think about it. It says half the perimeter. Well, what's the perimeter of a square if the side is X? 4x, right? What's half of 4x? 2x. That's what we got. The derivative was 2x. So all this verbiage, show that the rate of change of the area of a square with respect to its side, all of that was 2x, is half the perimeter. Half of 4x is 2x. So there it is. So all that verbiage boils down to half of the perimeter is 2x. What about all this other stuff, though? Try to explain geometrically why this is true by drawing a square with side length x, square with side length x, and increasing it by an amount delta x. How can you approximate the resulting change in area delta A if delta x is small? Okay, so what does that mean? So here's my original x by x. Okay, increase the length by delta x. Okay, now that means you still want it to be a square. So this goes up by delta x, this goes up by delta x. So the change in area is what I have in red. Okay, that's only the delta A. The delta A, the change in area, is this piece, and this tiny little square here, right? So delta A is the area of this rectangle, x delta x, plus the area of this rectangle, x delta x, plus the area of this tiny square, delta x squared. Okay. These two combine to be 2x delta x plus delta x squared. Okay. X delta x plus another x delta x is 2x delta x. Okay. If I divide both sides by delta x, I have delta A over delta x is 2x plus delta x. And there we go. They're trying to say explain geometrically. So let delta x approach 0. If this delta x approaches 0, that means we're getting really, really close to x, right? That's what we always do in calculus. Make this real small, make this real small. Okay. So what happens to this expression as delta x approaches 0? All that we have left is 2x plus 0 by plugging in, which is 2x. Okay. So in the limit, yes, we do have dA dx. After all, what is dA dx? It's delta A over delta x as delta x approaches 0. So we do get 2x. So the derivative is 2x, and that seems to be borne out by what we did here geometrically. Okay. So that's what's happening with that one. All right, so that's number 11. Next one I was going to show you is 13. A lot of 13 is stuff almost like back in 2.1. Find the average rate of change of the area of a circle with respect to the radius as r changes from 2 to 3, 2 to 2.5, 2 to 2.1. So remember way back in chapter 2, I think it was, you had a fixed point, right? 2 was fixed. Notice 2 is fixed, and you start off at 3, and then you got closer, 2.5, and you got closer, 2.1, right? So you're looking at the progression of the average rate of change. Back in 2.1, that was a secant line, right? Secant line. And we're using that to approximate the slope of the tangent line. That would be the instantaneous rate of change. So instantaneous rate of change, that's a derivative. All right. Do I have time to do that? Yeah, I have time to do that. We're going back to this picture. This thing, right? Fixed a point P, and then Q got closer and closer and closer, coming from the left and also coming from the right? Okay. So that's what we're doing here, but in this particular case, it looks like we're only coming one-sided. We're approaching 2 only from the right side. 2 to 3, delta x is 1. 2 to 2.5, delta x is 0.5. 2 to 2.1, delta x is 0.1. So it's getting closer and closer. All right, so I made a little chart. R, and area is pi r squared, right? So I plug into pi r squared. Okay, so the key numbers I need are 2, 2.1, 2.5, and 3. Okay, so I plug in 2, 4 pi. Plug in 3, 3 squared is 9, 9 pi. And 2.1 squared is 4.41 times a pi. It's better now not to multiply out that 3.14, just leave it as pi. And 2.5 squared is 6.25, so 6.25 times pi. Okay, so for the average rate of change, it's just y2 minus y1 divided by x2 minus x1. It's a slope of a secant line. We did that back in chapter 2. All right, so I take the numbers from 2 and 3. So 9 pi minus 4 pi, that's y2 minus y1 divided by x2 minus x1. 3 minus 2. So 9 pi minus 4 pi divided by 3 minus 2 comes out to be 5 pi. That would be the slope of the secant line. 2 to 2.5. So I'm using this and this. x1, y1, x2, y2. So y2 minus y1 divided by x2 minus x1. So 6.25 pi minus 4 pi divided by 2.5 minus 2. Punch it in your machine, 4.5 pi. And then 2 to 2.1, those two numbers are really, really close. So this would be a better approximation of the slope of the tangent line, i.e. the instantaneous rate of change. So instantaneous rate of change means derivative. Okay. It's like finding the average rate of change if you're going from 2 to 2.0000001. That is practically the instantaneous rate of change. Okay. So 2 and 2.1, I'm using 2 comma 4 pi and 2.1 comma 4.41 pi. All right, so y2 minus y1 divided by x2 minus x1. So 4.41 pi minus 4 pi divided by 2.1 minus 2 comes out to be 4.1 pi. All right, and then just notice the pattern way back in chapter 2. 5 pi, 4.5 pi, 4.1 pi. What seems to be the pattern? It looks like we're getting very close to what? It looks like 4 pi. Okay, now, can we prove it's actually 4 pi? Yes. The instantaneous rate of change is the derivative. Okay. So what's the derivative of pi r squared? Remember, pi is a constant, so 2 pi r. So a prime is 2 pi r. Now you plug in 2, because we're trying to find a derivative at 2. A prime of 2, 2 pi times 2, 4 pi. Makes good sense. So intuitively, we thought it should be 4 pi. If you look at the pattern of the slopes of the secant lines, the average rate of change, 5 pi, 4.5 pi, 4.1 pi. So, okay, it looks like it's going to 4 pi. And what do you know? It actually is 4 pi, just as we expected. Okay, now what about the rest of it? Show that the rate of change of area of a circle with respect to its radius at any r is equal to the circumference of the circle. Okay? You may have noticed that when I took the derivative. All that means is, what's the derivative of pi r squared, the formula for the area? 2 pi r, which is the formula for the circumference. Okay? So all of that means, here's the formula for the area, right? Take its derivative. You get the formula for the circumference of a circle, 2 pi r. That's all. So the circumference is a prime, 2 pi r. Now, again, this is one of those, can you try to show that geometrically why this is true by drawing a circle whose radius increased by amount delta r? How can you approximate the resulting change in area if delta r is small? Okay, so same thing, let me show you the geometry. Okay, so here's a circle. I increased it by delta r. Okay, so here's r plus delta r. So the increase in area is what I have shaded in red here. Okay. Now, imagine you cut it. You cut that with the scissors and open it up. Okay, you get something which almost looks like a rectangle. It's not quite a rectangle, right? Because the inner radius and outer radius are not quite the same. But if delta r is really, really small, okay, then the picture looks more and more like a rectangle, right? Can you imagine if you have this picture and you cut it and open it up, okay, then this length is 2 pi r, right? It's the circumference. And this height is delta r. So delta A is approximately base times height, 2 pi r divided by delta r, right? So one more time, if I take this region that I'm trying to find the area of, no inside part, just the outside, the delta A change in area, cut it, open it up, it looks sort of like this. You say, that's not a rectangle. Yeah, but if delta R is very small, it looks more and more like a rectangle, right? It's very rectangular-ish. It looks more like a rectangle in the limit. Okay, so base times height. Base is 2 pi r. Height is delta r, little change in radius. Okay, so delta A is approximately 2 pi r delta r. If I divide both sides by delta r, it looks like this. Delta A over delta r is approximately 2 pi r. The approximation gets better and better and better as delta r approaches 0, to the point where we say, okay, dA dr is exactly equal to 2 pi r, because in the limit, we do have a rectangle. So we can say dA dr is 2 pi r. Okay, so that's how that one works. 13. Okay, so that's that one there. Okay, I'll just do a couple more and then I think I'm done. Okay, I might just give you an introduction to the next section, but I won't do too much. 15, please. A spherical balloon is being inflated. Find the rate of increase of surface area, S is equal to 4 pi r squared, with respect to the radius r, when r is 1 foot, 2 feet, and 3 feet. What conclusion can you make? Okay, so here's a formula for the surface area of a sphere. S is 4 pi r squared. So rate of increase of surface area, that means derivative. I guess you can say ds dr. And then plug in 1, 2, 3. So here we go. S is equal to 4 pi r squared. ds dr, the derivative. Remember, 4 pi is a constant. Pi is a constant, 3.14, blah, blah, blah. So 4 pi is a constant. So the derivative is 2 times that. 2 times 4 pi is 8 pi r. Okay, now they tell me to plug in 1, 2, and 3. Plug in 1, 8 pi. Plug in 2, 16 pi. Plug in 3, 24 pi. Okay, what are the units? Okay, to find a unit, you just give the units of the numerator over the units of the denominator. So it's square feet per feet. Okay, I know the unit sounds weird. It's square feet per feet. 16 pi square feet per foot. 24 pi square feet per foot. That means if I increase the radius by 1 foot, I increase the surface area by this much. Okay, so what do we notice? As r increases, ds dr also increases. Okay, so when I increase the radius, the rate of increase of surface area also goes up. Okay, so I don't know if you think of a balloon. Well, I don't know if a lot of balloons are spherical, but pretend they're spherical. I've seen spherical balloons. As you keep blowing up the balloon, the rate of increase of the surface area gets bigger and bigger as time goes by. You get much more surface area further on down the line than you do at the beginning, so to speak. Okay. All right, then the last one is 19, and then I'm basically done. Okay, 19. The quantity of charge Q in coulombs that has passed through a point in a wire up to time where t is measured in a second is given by Q of t is this formula. Okay, t cubed minus 2t squared plus 6t plus 2. Okay, find the current when t is 0.5 and when t is 1. Okay, so they don't say it here. Those of you that have had physics or electricity and magnetism, okay, the current turns out to be the first derivative. Okay, so this is the charge function Q of t. The current is number of coulombs passing at a certain time. Okay, so Q prime or dQ dt, the rate of change of charge with respect to time. Okay, so that's considered current. Okay, so you have the current, like the current that flows in electricity, or the current in a battery, the current that goes in the car or whatever. Okay, that's the rate of change of charge with respect to time. Okay, so you take the derivative. So the derivative is 3t squared minus 4t plus 6. So this is something called current. Okay. Rate of change of charge, number of coulombs. They use C for coulombs. Do they have it here? Yeah, coulombs. Coulombs. Rate of charge. Okay. Think of it, the more electrons, the more coulombs you have. Okay. That's one way of thinking about it. So now we're talking about current. Okay, the unit of current is the ampere, or amp for short. You've heard of 10 amps or 5 amps or whatever. It's 1 coulomb per second. Okay, how much charge passes through a certain point every second. I should just plug in 0.5 and 1. So no big deal. So just plug those in. I'll let you do that on your own. So plug in 0.5 here and here. You get so many amps. And you also plug in 1. Maybe I can do 1 in my head. 3 minus 4 plus 6, 5. Okay, so when you plug in 1, you get 5 amps. Now, the part that's a little bit tougher, so I wasn't going to do it. I was only going to talk about it, let you figure it out. At what time is the current lowest? Current lowest, you are minimizing the current function, which is this. So don't look at the original anymore. Just pretend it's not even there. You're looking at this. Okay. What is the shape of 3t squared minus 4t plus 6? Now, we're used to having x, but even if it's t, because it's a squared, it's a parabola. It opens upward because my a is positive, so it opens upward. So I'm trying to minimize this quantity. It's a parabola. So if I'm trying to minimize this quantity, I want the vertex, right? It's U-shaped. Okay, its shape is going to be U-shaped. So I need to find where is the lowest point. Okay. Now you had pre-calculus techniques of finding the lowest point of a parabola. Okay, there's even a formula for that. Okay, but I want you to start thinking in terms of calculus. Okay, I know the shape is U-shaped. It's something like this. Right? One more time. How do I know? It's of the form AT squared plus BT plus C, which is parabolic. Okay, my A is positive, so it opens up. If my A were negative, it would open down. Right? So how do I find the vertex? Well, at this lowest point, what's the slope? Slope is 0. We'll use that theme quite a bit when we get to chapter 4, the next chapter. Okay? But one way you can find the lowest point or the highest point, if you have a maximum point also, the slope is 0. We'll use that a lot in chapter 4. Okay, so I want to find out when is the derivative of this function equal to 0. Okay, so you find the derivative of the current. The current itself is a derivative, which means you want q double prime set equal to 0 and solve for t. Okay, so that's as much as I'll say about that one. So in other words, you take the derivative of the current, i.e. the derivative of the derivative, which is the second derivative. So you take q double prime, set it equal to 0, solve for t. Okay, and that's very easy. You can do that. So to differentiate that is very easy. Okay, so I'll let you do that. And then just set it equal to 0. Okay, so that's what you do for that one. All right, so that's basically it. As I think I mentioned on Friday, it was not going to take me that long to do 3.7. So yeah, I am done with 3.7. I've already done quite a few of these problems. Okay, so what's up with 3.8? So I'll just give you a brief introduction to 3.8, and then I'm done. And I'll let you ask questions if you have any. But 3.8 is something you've done before. Exponential growth and decay. Something is growing exponentially, something is decaying exponentially. And I believe you had some of that probably in pre-calc, maybe even way back in intermediate algebra, you had some of this kind of stuff. All right. What's this dy dt equals ky? Okay. In some of the word problems, these are word problems, they're going to say the rate of change of a function is proportional to the amount present. Okay, you don't have to write that down, but we'll see that in the language. Okay, the derivative, rate of change derivative. Okay, that k is a constant of proportionality. You did a lot of that in intermediate algebra. So that tells you it's proportional to y, which is the amount present. Okay, so they have here y of t, the value of a quantity at time t, and if the rate of change of y with respect to t is proportional to the size y at any time. Okay, so that's what they're saying. dy dt is ky. Okay, so it's a law of natural growth or law of natural decay. Okay, very technically, this is called a differential equation. Okay, don't get scared by that, but there's a derivative and there's an equation. Okay, some of you need to take a course called differential equations. In fact, the highest course normally you can take at a community college is a course called differential equations. Okay, and I know some of you have to eventually take differential equations. The whole semester are equations that have derivatives. Okay, and you've probably seen something like this before. Okay, the only solution, you don't have to remember this, but the only solution to the differential equation dy dt equals ky is this: y of t equals y0 e to the kt. Okay, quite often we're not going to use all these letters there, but sometimes we just say y equals y0 e to the kt. Okay, k is a constant, okay, and y of t is y0 e to the kt. And that's actually not that hard to show. Okay. Let me start off with something like this. Y equals, let me call it c e to the kt, where this is your y0. Y equals y of 0. They can write the 0 like that, or you can subscript it. Okay. It's an initial amount. C is a constant, k is a constant. So what's the derivative of c e to the kt? Well, it's c e to the kt. Then by the chain rule, it's times the derivative of kt, which is k. So it's k times all of this. But all of this is just the original y. So there it is. There it is. Y prime equals ky. So dy dt or y prime equals k times y. So the rate of change derivative is proportional to the amount present, k times y. Okay, you can put this on your cheat sheet if you wish. You can put this in your cheat sheet. Okay, so y of 0, y parentheses 0, you can write it as y0 like that. That's a constant. That's the amount at the start. That's the starting amount. Okay, so starting amount. Beginning amount, y0, e to the kt. If k is positive, it's a growth situation. If k is negative, it's decay, like population decay, radioactive decay, situations like that. Okay. Now, this section is pretty much all word problems, as you can see here. Right? But let me just show you the language. Okay, and this is also for the benefit of those of you that don't have this, and so if you just want to look at the video later. But the language: a population of protozoa develops with a constant relative growth rate of 0.7944 per number per day, blah, 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 blah. So that tells you, you're going to use the formula. Okay, on day 0, the population consists of 2 members. Find a population after 6 days. Okay, so you're going to end up using this thing, right? So that's going to show up. And there's other situations like that also. Okay, bacterial growth. Okay, so the cell culture is growing. How much is going to exist after so many hours? When will the population reach 10,000, right? Would be the answer. Questions like that. Okay, so world growth, population growth involves stuff like that. And then in a decay situation, for decay, you have situations like that. Here's a chemistry reaction. N2O5 goes to 2NO2 plus 1/2 O2. So you chemistry people know you've seen chemical reactions like that. Okay, so there's a negative there. That means there's a decay situation. So the amount of N2O5 is decreasing as time goes by. Right, so they ask you all kinds of questions about that. And then we also have questions involving half-life. Okay, you've probably heard of half-life before. So when you have radioactive decay, right, the half-life is the amount of time it takes for a substance to reduce to half its original amount. Okay, so let's say for number 8, strontium-90 has a half-life of 28 days. So every 28 days, you have half the amount of strontium-90 that you had before. That's the way radioactive decay works. So we'll have some problems involving that. Okay, so that's just an introduction of what's going to happen for this. Okay, so I'm basically done, folks. So let me stop the share, check the chat real quickly, and let's see. 3.5, 21, and 51 were asked for. Okay, let me see if I have time for that. .5, 21, and 51. Okay. Now let me see if I can get that in the last few minutes we have. See, Dorina, you asked a question. I'm not quite sure what you mean by that, or you can send me an email about that. I'm not sure what you mean by is there a Discord for the class. So send me an email. I'm not sure. Sorry. Not quite sure what you meant by that. Okay, 3.521. It's better if I have a clipboard here. F of x plus x squared f of x cubed equals 10. F of 1 equals 2. F of x plus x squared, f of x cubed equals 10. Okay, so this is like y. You pretend that this is y. So let's differentiate implicitly. F prime of x plus product rule, first function, times the derivative of the second, 3 f of x squared times f prime of x, plus second function times the derivative of the first, 2x, equals the derivative of the right-hand side, 0. So let me see if I did that right. F prime, product root, x squared times 3 f prime of x, plus that. Okay, and now I just plug in 1 everywhere. Okay, so f prime of 1 plus 1 squared times 3 times f of 1 squared times f prime of 1 plus f of 1 cubed times 2 times 1 equals 0. 1 there, 1 there, 1 there, 1 there, 1 there, 1 there. Okay, f of 1 they told me is 2. So put a 2 there, put a 2 there. F prime of 1 is 1 squared is 1. So let me see. 3 times 4. Is that right? Did I do that right? 3 times 4, so 12. 12 f prime of 1 plus 2 cubed is 8. 8 times 2 is 16. So if f prime of 1 plus 12 f prime of 1, that's 13. F prime of 1 equals negative 16. So f prime of 1 is negative 16 over 13, unless I made a mistake. I think that's that. Okay, and do I just have enough time for 51? Yeah, maybe. Yeah. Okay, 51. Y equals inverse sine of 2x plus 1. So take the derivative of inverse sine, you go 1 over square root of 1 minus this thing squared. And then times the derivative of the inside, which is just 2. So 2 over radical 1 minus 2x plus 1 squared. And for now, I'd say you can just leave it like that. I mean, you could multiply it out, but maybe the back of the book multiplies it out, but no need to for this one, I would say. Okay. All right, and I think that's about it. All right. Okay, so we're done for the day, folks. So tomorrow I'll get started with the next section. Remember, Thursday, there's no classes at all, not just for my class, but no classes at all for CSM because it's flex day. All right, that's it, folks. So have a good day, and we'll see you next time. Okay, bye, everyone.
Thank you.
Bye.
Bye. Thank you.